Technology has increased the vision of pilots by developing far-seeing tools, such as weather radar, wind shear radar, TCAS, and other avionics systems. Weather radar is just that, a pilot's tool, an extended set of eyes that can let you, the pilot, see hazardous weather conditions long before you encounter them. The purpose of this program is to instruct pilots in the operation of the Bendix ARINC 700 series airborne weather radar system. In this program, we will provide you with the following information: a basic understanding of radar operation, a description of how to use weather radar to detect and avoid dangerous weather cells, a set of suggested guidelines for using a weather radar throughout a typical flight. The word radar is an acronym for radio detection and ranging, or in other words, finding and locating targets by means of radio waves. A receiver-transmitter unit of a radar generates pulses of microwave energy which are sent to its antenna. At the antenna, these pulses of energy are focused into a beam. The beam is similar to that of a flashlight's beam. When these pulses of energy strike an object, some of the pulsed energy will be reflected back to the radar. The amount of energy which is reflected back to the radar is dependent upon the target's material and its surface orientation. Some objects are much better radar reflectors than others. A raindrop is basically spherical in shape and is a fairly good radar reflector. Snowflakes and dry hail, on the other hand, have very complex structures and do not favor radar reflection. The reflected radar signals, which are called radar echoes, are displayed on a scope called a Plan Position Indicator, or PPI. The radar display appears as a top-down view of the targets being scanned by the radar's beam. The pulse of energy which is transmitted from the radar antenna is in the form of electromagnetic microwave energy. Its frequency is 9.3 billion cycles per second. It travels through space at the speed of light. The distance to a target is determined by measuring the round-trip travel time of the pulse. The direction to the target is the direction the antenna is pointing when it receives the target's echo. The Bendix ARINC 700 series airborne weather radar installations contain 5 basic components. A receiver-transmitter unit for transmitting, receiving, and processing the radar energy. A waveguide which guides the microwave energy back and forth between the antenna and the receiver-transmitter. An antenna which focuses the microwave energy into a beam and continually scans it from side to side, and has the ability to point it at a specific elevation angle. A radome, which is a protective covering for the antenna that allows the pulses of microwave energy to pass through. And a display unit, which displays the process radar echoes as well as provides a mounting point for the system's controls. In order for you to operate a weather radar properly, it is essential that you have an understanding of the characteristics of a radar beam. The radar beam searches a horizontal slice of airspace 90 degrees to each side of the aircraft's longitudinal axis. The size of the antenna is the main factor that determines the width in degrees of the radiated beam. The larger the antenna, the smaller the beam width. The type of antenna normally used by large commercial aircraft is round with a 30-inch diameter. It produces a cone-shaped beam 3 degrees wide. Because the radar beam is just like a flashlight's beam, the radar beam's diameter enlarges as it travels outward into space away from the antenna. For those of you who are mathematically inclined, the beam width diameter can be calculated at a given range using the following equation. Beam width in feet is equal to the range in nautical miles times the beam width in degrees times 100. As an example, if the range is 10 nautical miles and the beam width is 3 degrees, the beam is 3,000 feet wide. At 20 miles, it's 6,000 feet wide. While this is good background information, proper use of weather radar, as you will see later, requires no calculations at all. One of the effects of beam spreading is to reduce the radar's target resolution capability. That is, its ability to separate two targets at the same range, but located at slightly different viewing angles. When the distance between the two targets at the same range is less than the diameter of the beam, the two targets merge together on a display and appear as one. As the aircraft approaches the targets and its beam diameter at their location becomes smaller than the distance between them, they are resolved as two separate targets. A stabilized antenna scans horizontally as the aircraft maneuvers. With the tilt control set to 0 degrees, the radar beam center is set at the aircraft's altitude and projects 1 1/2 degrees above and below the horizontal plane. The tilt control can be used to direct the beam plus and minus 15 degrees with respect to the horizontal plane. Some radar installations have a switch to disable stabilization. In other installations, this function is always enabled. Without stabilization, the antenna tilt angle is referenced to the longitudinal axis of the aircraft and will not be corrected by the gyro inputs during aircraft maneuvers. During maneuvers, heavy ground returns will normally be displayed. Antenna stabilization loses its effectiveness when the combined pitch, roll, and tilt angles exceed about 45 degrees. These limits can be exceeded during high pitch and roll maneuvers and will cause heavy ground returns to be observed on the display unit. Pilots who fly aircraft using conventional vertical gyros can be expected to experience some stabilization degradation during periods of acceleration. This phenomenon is due to precession errors developed within the gyro. These precession errors are caused by aircraft acceleration during takeoff and shallow bank turns of less than 7 degrees. The manual gain control is used to adjust the sensitivity of the radar's receiver. One application is to reduce the signal strength of strong target echoes so that they may be resolved on the display. By doing so, it becomes possible to determine the relative intensity differences between strong thunderstorms. As the gain control is rotated counterclockwise, the receiver's sensitivity is decreased. Manual gain must be left in the auto position to use the radar in a calibrated weather mode. The only time manual gain should be used in the weather mode is if you want to use it to evaluate the relative rainfall rate of 2 or more strong storms. When you are finished, return it to auto. If you forget and leave the system uncalibrated, you could get surprised by a dangerous undetected storm. As you observe weather targets on the radar display, you see them in their broadest dimensions. The higher the rainfall rate within a storm, the larger will be its radar reflection. When the radar system is in the weather mode, it's calibrated to display the different rainfall rates as different colors. Black is very light or no rain. Green is 0.7 to 3 millimeters per hour of light rainfall. Yellow is 3 to 12 millimeters per hour. That's medium rainfall. Red is 12 millimeters per hour and higher, or very heavy rainfall. Magenta indicates the presence of turbulence within the rainstorm. Some older EFA systems do not display magenta. Weather cells, which are very active, often called thunderstorms, have high levels of turbulence and excessive amounts of precipitation contained within them. Flight crews can learn to recognize these thunderstorms and assess their hazard potential by looking for the following characteristics. A rainfall rate anywhere within a cell displayed as a red color. The amount of danger a storm represents to an aircraft is strongly related to the rainfall rate within the storm. A storm which is displaying red rainfall can always be considered a threat to the aircraft and should be avoided. The existence of steep rainfall gradients. A steep rainfall gradient is defined as a rapid change in the rate of rainfall within the storm. A steep rainfall gradient is indicated when the distance between no rain and a red area is 2 miles or less. That condition indicates a highly active and dangerous storm. Anytime a steep rainfall gradient is observed, that storm should be avoided by a considerable margin. The rule of thumb is, the steeper the gradient, the greater will be the storm's associated turbulence. The shape of the weather cell. There are some distinctive storm shapes which are well known to represent dangerous storms. They are protruding fingers, scalloped edges, U-shapes, hooks, sometimes associated with tornadoes, thunderstorm development in a line, visual clues that can alert pilots to severe convective weather conditions are a storm moving in excess of 10 knots, a visible anvil shape at altitude, and frequent lightning. It's a good rule of thumb to avoid any storms with these characteristics by at least 20 nautical miles if possible. As a radar pulse of energy travels through a rainstorm, each raindrop scatters a small fraction of the pulse's energy. The more raindrops within the rainstorm, the more of the pulse's energy is lost to this phenomenon. An intense rainstorm will disperse all the available pulse energy within a very short distance, as little as a couple of miles. Once this occurs, the radar's ability to detect targets beyond that range is completely exhausted. This energy loss phenomenon is referred to as radar attenuation. Any targets that are in the path of the radar pulse but are not illuminated by that pulse because of radar attenuation are described as being in a radar shadow. Another cause of radar beam attenuation that crews should be alert to is attenuation resulting from a heavy sheet of water or the formation of an ice layer on the radome. These conditions will reduce system range performance and cause target intensities to be understated on the radar's display. The Bendix ARINC 700 series radars, when equipped with the Doppler turbulence detection option, are capable of detecting and displaying storm-related turbulence in addition to the rainfall rate display. Turbulence within a rainstorm causes the raindrops to travel in a very erratic path as they plummet toward Earth. The turbulence detection radar identifies these areas of moderate to strong turbulence by measuring the change of the horizontal raindrop velocity from one transmitted pulse to the next. The system displays the areas of turbulence as a magenta overlay on the radar's normal weather presentation. On older EFA systems, turbulence is displayed as red. The turbulence display operates out to a maximum range of 40 nautical miles. Ranges in excess of 40 nautical miles may still be used while operating in the turb mode. On these longer ranges, the first 40 nautical miles operates in the turbulence detection mode, and the remainder of the displayed range operates in the normal weather mode. Manual gain control can also be used to help evaluate range cells for the presence of turbulence. The turb display is unaffected by manual gain. By reducing the gain, and therefore reducing the strength of the displayed range signal, any areas of turbulence will be dramatically highlighted. This tool can be especially useful on EFIS displays which do not provide the magenta color. Turbulence within a thunderstorm may be present in any part of the storm, not just in the areas of heavy rainfall. As a general rule, it is advisable to avoid any areas of green returns which include magenta. The turb mode cannot detect clear air turbulence because there is no precipitation present to reflect the radar signal. The primary purpose of weather radar is to identify and avoid dangerous weather before you are in it. To that end, a radar operator must be able to adjust the elevation beam angle of the radar and know exactly where it is pointing. The antenna elevation pointing angle, commonly referred to as the tilt angle, can be manually adjusted 15 degrees above and below the horizontal plane. This capability allows the radar operator to point the beam of the radar at the thunderstorms at various altitudes. Before describing some useful techniques for both tilt and range management, it's necessary to explain the reflection characteristics of thunderstorms. Thunderstorms come in two forms, frontal and air mass. Regardless of their type, they each have a typical radar reflection profile. The lower part of the storm, the section below the cloud base, is composed entirely of raindrops and is a good radar reflector. The section between the cloud base and about 18,000 feet also contains raindrops and is a good radar reflector. Above that altitude, the precipitation is frozen and is a poor radar reflector. In order to produce an accurate radar return from a rainstorm, the beam of the radar needs to be directed toward the lower 18,000 feet of the storm. Through tilt management, this goal can be achieved. Let's say the radar is being used on the 80 nautical mile range in the weather mode while at an altitude of 30,000 feet AGL. The goal is to keep the display relatively clear of ground returns while making certain that no weather cells go undetected in or near the aircraft's flight path. Start by using the tilt control to point the antenna down so that the ground return stripe can easily be identified. A tilt angle of -10 degrees should be adequate. The absolute value of the down tilt angle is of little importance. The key element in this procedure is to place the ground return stripe at a location where it can easily be identified by the radar operator. At -10 degrees, the center of the ground stripe will be located at approximately 30 nautical miles. At this point, you can think of the radar's beam as illuminating the Earth's surface in a manner similar to the way a searchlight mounted on the front of the airplane and pointed at a similar angle would illuminate the ground in front of it. Now slowly increase the tilt angle to lift the beam. As the beam is lifted, you'll be able to see the ground stripe reflection moving further out in range. Weather radars typically scan from one side to the other side in about 4 seconds, so be patient and make the tilt adjustment slowly. Continue to move the beam outward until only the outer edge of the displayed range contains ground returns. Let's say about 5% of the display. That's it. That's all that is necessary to adjust the radar for proper tilt management on any display range. Now, as the aircraft moves forward, if rainstorms move within the displayed range, their highly reflective bottom section will encroach into the beam's path and will be presented on the display unit. As you fly toward a storm, its display will move forward of the displayed ground returns, creating an easily identifiable shadowed area behind it. At high altitudes, over 25,000 feet, as you fly closer to the storms, depending on their intensity, the display presentation may change colors or disappear entirely from your display because the beam is overscanning the most reflective part of the storm. If, as you fly, you wish to keep track of a storm that you are beginning to overscan, reduce the display range setting and repeat the same procedure. With a little practice, you'll be able to set up a display range very quickly. Letting the radar beam overscan a storm which is off to the side of your flight path is okay. It is, however, ill-advised to fly through the clear air above a storm cell or penetrate the less reflective storm top. That area of the storm can be very dangerous due to unstable air and the possible presence of hail. Overscanning by setting the tilt too high is undoubtedly the most common mistake pilots make when operating a radar. If you change altitude, consider the geometry of the scenario. If you descend, you need more up tilt to display the correct radar picture. And if you ascend, you need more down tilt. You should adjust your antenna tilt each time you significantly change your flight altitude. Coupled with a requirement for good tilt management skills is a requirement for good range management skills. Range management means to choose the radar display range that is proper for your flight altitude. If your flight path is below 18,000 feet AGL and you use the recommended tilt management procedure, you can use any display range and not be in danger of overflying a dangerous storm. In that case, simply select a range which will give you adequate warning time so that you can make an avoidance maneuver in a timely manner. At the higher altitudes, it's important to remember that you are flying above the most reflective part of the storms, and consequently, you will require a significant down tilt to make certain no storm goes undetected. If you ever find yourself in doubt about whether or not the tilt position is correct after you have made a range change, move the tilt angle down briefly and readjust the beam to give the correct amount of ground return. The best way to develop good tilt and range management skills is to practice them in good weather. Once you have gained these skills and refined them, it will be a simple matter to adjust the tilt and range controls for safe weather avoidance. At long distances, the energy within the pulse spreads out over a large area. At 100 nautical miles, the beam is 30,000 feet in diameter. That means that at least half of the pulse energy is going to overshoot the most reflective part of a storm. A secondary effect is that, at long viewing distances, the Earth's surface starts to block targets which are beyond about 150 nautical miles. The combined effect of these two factors makes detecting rainstorms at long distances more difficult. If rainstorms are detected at long ranges, say over 100 miles, regardless of their displayed intensity, consider them significant storms and make course deviations as early as possible. Ground mapping refers to the process of using the Earth's surface as a radar target. The radar will ground map in either the weather mode or the map mode. The main difference between the two modes is the way the radar processes echoes. To use the radar to ground map, select the map mode and adjust the antenna tilt control downward until the terrain area of interest is presented on the radar display. The larger the downward tilt angle, the closer the detected terrain will be to the aircraft, and the smaller will be the illuminated ground area. This reduction of the illuminated area is due to beam width effect. The radar beam width in the map mode is 3 degrees wide, the same as in the weather mode. Like precipitation targets, terrain targets exhibit different reflectivity qualities. It is this difference in reflectivity that produces a unique map. The display will provide a map view of prominent landmarks such as cities, lakes, rivers, shorelines, and other terrain features that lie within the beam of the radar. Because the intensity of ground returns varies widely based on the angle the radar's beam is illuminating the ground, the manual gain control may be useful in obtaining an interpretable ground map display. You should generally fine-tune a map display by varying both the gain control and the antenna tilt angle settings until the presentation is satisfactory. Whenever possible, it's good practice to sharpen your mapping skills on known ground targets in good visibility. When attempting to map sea returns, be aware that calm water provides a very low radar reflection. It acts like a mirror and reflects the pulses forward and away from the receiver. The same is true when viewing the sea from a direction parallel to the waves. A much stronger reflection can be observed when viewing the sea in the up and downwind directions, the upwind being the strongest. Sometimes a city may be mistaken for a weather cell while operating in either the map or the weather mode. This can happen because a city has the same general appearance on a radar display as does a storm cell. It has a red core area, downtown. It has a yellow outskirt, the suburbs, before it tapers off green and broken black, the outskirts of town. If you learn to look for a radar shadow, however, you can always differentiate between a storm and a city. That is because the city does not extend into the sky very far, and therefore does not cast an appreciable radar shadow. Another interesting ground target is a mountain. It has a crescent shape and a shadow behind it. It is slightly more difficult to identify as being a ground target than a city. Mount Hood, Mount Rainier, and Mount Shasta near the Pacific coast of the United States are good examples of mountains that are fairly isolated and look like isolated intense storms. Be very careful to know where they are located. If you adjust the radar beam angle to remove all ground returns from the display while maintaining a strong reflection from the weather cells, the radar display will appear as shown. You can see that the most intense part of the storm is hidden from view and dangerously understated. If you did not identify the crescent shape on the front edge of the storm cell and realize that a significant radar shadow is present, you might make the decision to fly toward the area which appears clear, an area that is, in fact, the most dangerous part of the storm. A powerful technique which will allow you to properly evaluate the weather conditions in this scenario is to adjust the tilt so that the radar's beam is directed toward the ground. This procedure allows you to identify the radar shadow which is being cast by the dangerous thunderstorm and take precautionary measures to avoid that storm. Extended areas of rainy weather sometimes contain embedded thunderstorms. If an aircraft is flying in this type of weather, its radar beam will be significantly attenuated by the extended intervening rain. This will reduce its overall range performance. If the beam of the radar is adjusted to only display rain echoes, the display will appear like this. As the aircraft approaches the embedded thunderstorm, the display will change to this. Seeing this presentation, you might not realize that the crescent shape of the outer edge of the weather pattern is the result of a thunderstorm attenuating the signal and creating a radar shadow. If you mistakenly interpret that area as a clear zone, you will probably make the wrong decision to fly toward it. If, on the other hand, you adjust the radar tilt to direct the beam toward the ground, you will see this radar presentation. Now, when you approach the embedded thunderstorm, you will see the ground returns become shadowed and immediately make the decision to fly away from that area. Under these weather conditions, always fly toward the displayed ground returns. Although this procedure works well in extended rainy conditions, we cannot overemphasize that weather radar should be used for weather avoidance, not penetration. The weather radar industry uses the term spokes to represent any presentation on the radar display unit which resembles wagon wheel spokes. The main cause of spokes is usually interference from powerful military ground radar. This does not indicate a radar system failure. If you are uncertain whether the radar system is malfunctioning or if the spoke is being caused by an external source, change the heading of the aircraft slightly and notice if the heading of the spoke changes in the opposite direction the same number of degrees. If it does, it's external interference. Ignore it. While the aircraft is parked at the gate or taxiing in congested areas, keep the radar system in the test mode. Once the aircraft is clear of personnel and fuel trucks, set the mode control to the turb mode if available, otherwise the weather mode, and the range control to 10 nautical miles. Adjust the antenna tilt control to display ground returns as a confidence check. This procedure ensures that components not checked previously in the test mode are working properly. With the aircraft pointed so that the antenna can scan the intended departure area, scan that volume of space by slowly rotating the antenna tilt controls to +9 degrees while looking for convective weather. If the 10 nautical mile range is clear, repeat the operation for the 20 and 40 nautical mile ranges. Look for dangerous storm shapes while being particularly sensitive to crescent-shaped storms. Remember, crescent-shaped storms are likely to be hiding dangerous weather. If your evaluation of the takeoff area indicates a safe zone, leave the range set to 40 nautical miles and adjust the tilt control to +4 degrees for takeoff and initial climb-out. On aircraft that use conventional gyros, set the tilt to +7 degrees instead of +4 degrees. This additional +3 degrees compensates for the 3-degree acceleration error caused by precession of the gyro during acceleration. Precession error affects both pitch and roll during takeoff and climb-out. For aircraft with conventional gyros, the acceleration error will continue until the aircraft reaches a steady-state airspeed. Once the aircraft is in a steady climb, it will take approximately 3 minutes for the vertical gyro to stabilize and provide the radar with a correct attitude reference. As a rule of thumb, on climb-out, pilots should reduce the initial tilt setting by approximately 1 degree for each 10,000 feet of climb, or until ground returns appear on the outer edges of the scope. Once the ground returns are presented on the outer edge, small adjustments to the tilt can be made to maintain that presentation. Around 20,000 feet, switch to the 80 nautical mile display range and set the antenna tilt controls to 10 degrees down. Slowly rotate the antenna tilt control up while watching for weather cells until ground is being only lightly painted on the outer edge of the displayed range. As the climb proceeds, continue to make small adjustments to the tilt as necessary until the aircraft reaches cruise altitude. This procedure will correctly point the antenna beam and create a zone where no storms can go undetected. Some pilots prefer to use the 160 nautical mile range at cruise altitude. If that is your preference, switch the radar to that range and repeat the tilt management procedure. If during the flight a radar system is suspected of having poor range performance, a confidence test should be initiated. A radar system that is functioning correctly should display ground returns out to a distance of at least 160 nautical miles. To perform this test, the aircraft needs to be at an altitude of at least 21,000 feet AGL. If the radar will display ground returns at that distance, it will display weather correctly. Whenever an en route storm is being evaluated, aggressive use of down tilt is necessary to direct the beam into the lower 18,000 feet of the storm. A subtle form of overscanning can result if a low-altitude thunderstorm is rapidly building. Some convective storms grow at rates of up to 8,000 feet per minute and can rise up under your flight path as you approach them. If convective activity is high in your area of flight, it's a good idea to lower the beam from time to time to look for rapidly developing storms. A blind alley or box canyon situation can be a dangerous trap for pilots that habitually fly with the radar on a short range of 40 nautical miles or less. The short range returns show a corridor between two areas of heavy rainfall. The long range setting shows the trap. Always switch to the long range before entering such a tempting corridor. When flying over water, where you cannot always be guaranteed an adequate ground reflection, the following tilt settings are suggested. At a range of 40 nautical miles, 6 to 7 degrees down. 80, 3 to 4 degrees down. 160 nautical miles, 2 to 3 degrees down. En route deviation should always be made upwind of a storm. Deviating downwind increases the chance of encountering hail and turbulence. You can expect turbulence 1 nautical mile downwind for each knot of wind speed at your altitude. As a general rule, you should avoid thunderstorms by the margins shown. On descent, in order to maintain the proper display presentation, it will be necessary to adjust the tilt up approximately 1 degree for each 10,000 feet of reduced altitude. Weather evaluation of the terminal area should begin at about 70 miles out. This evaluation should include aggressive use of the tilt controls to assess the intensity of any weather targets in the area. If a storm is located in or around the terminal area, adjust the radar's display range to emphasize the storm's location, and adjust the tilt control to direct the radar beam toward the bottom of the storm. By following this procedure, you will be able to observe if any radar shadow exists. If one does, fly away from it. On final approach, adjust tilt to 6 degrees up, using the 10 or 20 nautical mile range. This will allow the radar beam to safely scan the terminal area for weather activity, while eliminating ground returns and minimizing the radar workload. Evaluating weather should be an ongoing process until the landing is completed. Keep the radar display in your view and be prepared to initiate a go-around if threatening weather appears on the scope. This program has covered the following subjects: a basic understanding of radar operation, a description of how to use weather radar to detect and avoid dangerous weather cells, and a set of suggested guidelines for using a weather radar throughout a typical flight. It should be noted that the most important radar skill a pilot can possess is the ability to use the ground echoes as a reference point for proper tilt management. By learning to use the beam to observe the ground in good weather as often as possible, you will become familiar with its reflection characteristics. Having gained this familiarity, you'll be able to adjust the tilt angle of the antenna to make valid assessments of weather conditions. Remember, weather radar is a tool pilots have, much like extended vision, that provides significant warning of hazardous weather. Use this tool wisely, and it will add to the safety of your flight.